Okay, so we're going to move on to the next subject, which is internal flow. Okay, and we're going to focus primarily on liquids in pipes. I mean, or fluids in ducts. You know, something along those lines. But mostly circular pipes or circular ducts or circular tubes. There is a way to take what we're going to show here and um, generalize it to ducts or tubes of various cross sections, but we're going to focus on circular or cylindrical tubes, and if you're curious about that generalization, I can we can discuss it, but anyway, one of the first major topic that we have to sort of cover is the way there's a transition that happens in internal flow. Okay, for low flow rates, the fluid typically will remain what's called laminar, and laminar flow is exactly what it sounds like. The flow tends not to mix much with itself. So, if if a particle of fluid or a small region of fluid is located, say, in this section of the flow, it will remain in that section. So basically, the things don't mix. So things remain in layers. Okay. Um, so it's a highly orderly flow. So it looks kind of like this. You know, um, the layers don't mix. These streamlines don't cross one another. That sort of thing. And for circular tubes, the the velocity profile is parabolic, so it's related to the radius squared. Okay, and so another thing about this is that you'll notice that the average velocity might be something like, it's a significant amount less than the max velocity, right? So in fact, it comes out to be exactly one half. So this would be, say, U average, and this would be U max, and U max equals 2 U average. That's just a um, interesting side note, I guess. In circular pipes, this is only true in circular pipes. Okay. Then, at a certain flow rate, the fluid may transition into what's called turbulent. All right, and actually, under various other circumstances, could allow flow to transition into turbulent flow, and that is highly chaotic. So rather than stand nice and layered like this, a fluid particle down here, there's no saying where it's going to wind up. So if a fluid particle starts down here, it oscillates wildly, and through a series of eddies, and could wind up anywhere. As a consequence, momentum is transferred across the cross section quite well, right? So a fluid particle here has a certain amount of linear momentum in the x direction, and it as a consequence of all this oscillation and movement and mixing with the rest of the flow, all the momentum tends to equalize across the duct, and you wind up getting a very blunt profile. So in this case, the average fluid velocity would be just under the peak value. So in this case, there's no clear-cut correlation between the maximum and the average value, but they are very close together, much more so than was the case up here in laminar flow. And so we establish a parameter by which to determine, like when we're doing analysis, um, we need a way of determining whether or not the flow that we're going to be dealing with is going to be laminar or turbulent. All right, so we need a parameter to do this, and this parameter happens to be what's called the Reynolds number. And it has other various other. It's a very important non-dimensional value. It's a non-dimensional number. It's simply a number. Okay, and it's a ratio of certain fluid properties. Okay, but at its heart, it's essentially the inertial forces. So you have the density times the velocity, which is mass times velocity, momentum. So the inertial forces divided by any sort of viscous forces, which in fluid flow is represented by just the viscosity. Now, like I said, it's a dimensionless number. It has no dimensions. And so to get the dimensions right, I need a characteristic length. So I have kilograms per meters cubed. Then I have meters per second squared and Pascal seconds. To get the units to go away, I need meters on the top in the SI units. So we need a characteristic length. So this L represents a characteristic length, okay, for flow in circular tubes. This characteristic length is usually taken to be the diameter, but the Reynolds number has other definitions depending on the situation. So this characteristic length could be the length along a flat plate. It could be, it could be any number of things. Like the span of a airfoil is sometimes taken to be the characteristic length, or maybe not the span, but the core. It's called the chord of an airfoil. The diameter of a circular, like a ball flow, that might come out to be the characteristic length would be the diameter in that as well. But the characteristic length is oftentimes used as a subscript for the Reynolds number itself. So the Reynolds number using the diameter as a characteristic length would be given by the density times velocity times the diameter divided by the viscosity. Okay. Now, the transition between laminar and turbulent is probably best illustrated via a video. Okay. So the way this happens, these guys are going to introduce some dye here, and they have a little obstruction. And so basically, we have fluid flow over this little this little obstacle, and where the dye is placed. Okay. Now, what happens is there's an obstruction here, right? And so there's a disturbed portion of the flow field here. But at slow flow fields, the Reynolds number is low, so the viscous forces are very high compared to the inertial forces. Okay. And as a consequence, any sort of perturbation that occurs at this obstruction damps out quickly. The viscosity damps out any of those oscillations. All right, it's a friction force. Viscosity is essentially a parameter related to essentially friction. So the fluid, the friction in the fluid turns those rapid oscillations or those oscillations into heat and damps out those oscillations. Okay, so that's at low flow rates. As the flow rate increases, those inertial forces are increasing. As the velocity increases, the density times the velocity is increasing. So the inertial forces are increasing as well. And as a consequence, at some point, they start to overcome those viscous forces. So these oscillations that begin start to persist for a little while, and you can get these oscillations. These are somewhat periodic, right? You have a somewhat periodic vortex shedding is what it's called. Um, you know what I mean? So the inertial forces are starting to be roughly approximately equal to those viscous forces, and so these perturbations are allowed to persist. Um, okay. Then at some point, you enter what's essentially fully turbulent, where those inertial forces start to overcome any viscous forces, and the fluid flow will become extremely disordered. All right. So you'll start to see that transition here in a second. There's a lot of mixing going on. You even start to see some backward flow there. This was probably evident earlier than what you're able to illustrate it here, but it's much more evident here because the mixing between the flow coming over the obstruction with that region that was um, uh, realizing some, you know, some backwards flow. So the upshot here, the upshot here is that at some critical Reynolds number, at some value of the Reynolds number, the flow becomes turbulent. Okay, that value of the Reynolds number is called the critical Reynolds number. All right. So as the flow rate, as the Reynolds number, and you can look at it, the Reynolds number is going to increase as a function of the velocity. Okay, so as that velocity increases, the Reynolds number increases, and then when the Reynolds number approaches the critical value, um, so the RE critical for circular tubes, that critical Reynolds number is something like this. So below about 2300, so this is a very approximate sort of empirical situation, all right? This is going to be laminar flow. Meaning that if there are any perturbations in the flow, like you go through a fitting or something like that, that those perturbations will not persist very long, okay? Then between about 2300 and 4000, this is called transitional. Meaning that could be that situation where these perturbations will persist in some cases, and so you wind up going back and forth between laminar and turbulent, perhaps. You sort of oscillate between the two. Or it's that periodic sort of flow that you get. And then for Reynolds numbers greater than 4,000, this is going to be fully turbulent. And so these values are sort of empirical. They've been, observed to be the case for circular tubes. All right. If we had a different situation, you would have a different critical Reynolds number. Okay. All of these are the Reynolds number using the diameter as the characteristic length. Okay, so I guess the critical Reynolds number would be like 4,000 or something like that. It's not exactly a single value, so there's a transition period between 2,300 and 4,000 for circular tubes. And this varies. This is not always the case, right? So the critical for instance, for flat plates, for flow over a flat plate, um, so we have a flat plate, we have a velocity profile that looks something like this. This is usually taken to be the x value, so along the flow. And the critical value and the critical Reynolds number in this case is typically taken to be a much larger number. So in this case, we use the Reynolds number using x as the characteristic length. So the Reynolds number actually changes as a function of the length along the a length along the plate as well as the velocity. And so that is, oops. And the critical Reynolds number for that is like 5 times 10 to the 5th, which is like what, like 100,000, 500,000, so about 500,000. So for circular tubes, the critical Reynolds number is like 2,300, and for flat plates, it could be upwards of 500,000. And it's not unusual to have Reynolds numbers in times somewhere around 1,000,000, 10,000,000. Stuff like that. So these huge numbers are not uncommon when you're dealing with the Reynolds numbers, even for circular tubes. To have a Reynolds number on the order of 20,000 is not exactly unheard of. Okay, especially in like gases and tubes. This mu is a very small number. Even though density is not very large, the viscosity can be very, very small, and so Reynolds number can be very large, can get very large very quickly, and it's very difficult to maintain gases in laminar flow. They can barely be moving to maintain laminar flow.